Hello friends, myself Manish Joshi, welcome all of you on my YouTube channel. In this video, we will discuss about an important concept of chemical kinetics, that is integrated rate equation of gaseous first order reaction. Now, what is the need to discuss this topic separately from the integrated rate equation for first order reaction? हम लोगों ने फर्स्ट ऑर्डर रिएक्शन के लिए इंटीग्रेटेड रेट इक्वेशन पढ़ लिया था, फिर भी अब हम लोगों को वापस इसी फर्स्ट ऑर्डर इंटीग्रेटेड रेट इक्वेशन को गैसियस रिएक्शंस के लिए पढ़ रहे हैं. इट मीन्स दोज रिएक्शंस विच आर फर्स्ट ऑर्डर बट दे इन्वॉल्व द रिएक्टेंट एंड प्रोडक्ट इन गैसियस स्टेट्स. सो व्हाट विल हैपन व्हेन वी कंसिडर सच टाइप ऑफ केस? जब हम लोग गैसियस रिएक्टेंट और गैसियस प्रोडक्ट के साथ डील कर रहे हैं, तो क्या इंटीग्रेटेड रेट इक्वेशन नॉर्मल इंटीग्रेटेड रेट इक्वेशन फॉर फर्स्ट ऑर्डर से डिफरेंट होता है? अगर डिफरेंट होता है तो क्यों होता है, और नहीं होता है तो फिर इसको हम लोग सेपरेटली क्यों पढ़ रहे हैं? सो द आंसर ऑफ दिस क्वेश्चन इज दैट जनरली द बेस्ट रिएक्शंस occurs, or we can say normally the best phase to occur a chemical reaction, that is liquid state. And when we deal with the liquid, automatically we know that automatically we reached on the term concentration, because the concentration related to the liquids. And the same thing we have discussed in the integrated rate equation for first order, and the formula was there: K1 is equals to 2.303 upon T log A upon A minus X. A is their initial concentration, A minus X, that is final concentration. But when we introduce this case for the gaseous first order reaction, the scenario will be different, because for the gases we generally involve pressure, but the integrated rate equation which we have obtained for the first order reaction, that involve concentration. So to avoid the confusion between these two physical states, first order reaction either in liquid or in gaseous state, we have to discuss this topic separately. So in this video we will discuss the integrated rate equation for first order gaseous reaction. So dear friends, this is the integrated rate equation for gaseous first order reaction. Now suppose this is a typical example of a gaseous first order reaction, when a reactant A which present in gaseous state convert into the two product B and C. Both products are also present in gaseous state. एक रिएक्शन है जिसके अंदर एक रिएक्टेंट है जो गैसियस स्टेट में है, और B और C दो प्रोडक्ट हैं वो भी गैसियस स्टेट में है. Let Pi is the initial pressure of A and Pt be the total pressure at time t. Integrated rate equation may be written as K1 is equals to 2.303 upon T log Pi upon Pa. Pi will be replaced from initial concentration, Pa is the final replaced by the final concentration. So on the place of initial concentration and final concentration, we have introduced initial pressure and final pressure, where P is the partial pressure of A at time t. The partial pressure of A can be derived as follows. the total pressure PT will be PT is equals to PA plus PB plus PC as per Dalton's partial pressure law. The Dalton's partial pressure law says that when we have a non-reacting mixtures of different gases in a container, the total pressure imposed by the gaseous mixture on the wall of the container is the sum of partial pressure of all the non-reacting gases. So PT is equals to PA plus PB plus so the total pressure PT is equals to PA plus PB plus PC, where PA, PB, PC are the partial pressure of A, B and C respectively. Let the pressure of A decreases by x atm after time t. जैसे हमने स्टार्ट किया था ए से, तो ए जैसे जैसे प्रोडक्ट में चेंज होने लगेगा तो उसका जो इनिशियल प्रेशर होगा वो धीरे धीरे कम होने लगेगा, और सपोज हम मानते हैं कि उसमें से एक्स एटीएम प्रेशर जो है वो कम हो गया है. सिंस 1 मोल ऑफ बी एंड सी आर फॉर्म्ड फ्रॉम 1 मोल ऑफ ए, सो देन इंक्रीज इन प्रेशर ऑफ बी एंड सी विल ऑल्सो बी एक्स एटीएम ईच एज, क्योंकि बी और सी भी एक मोल ही बन रहा है एक मोल ए से, इसलिए जितना डिक्रीज ए के प्रेशर में होगा उतना ही इंक्रीज बी और सी के प्रेशर में होगा, इसलिए यहाँ पर हम लोग उसको एक्स एटीएम मानते हैं. सो अगेन ए कन्वर्ट इनटू बी प्लस सी एट टाइम टी 0, द स्टार्टिंग प्रेशर इज पी आई. The starting pressure of product will be 0 because at the time 0 there will be no product formed there. कोई भी प्रोडक्ट वहाँ पर नहीं बनता है, इसलिए वहाँ पर जो पार्शियल प्रेशर है वो 0 रहेगा. एट टाइम टी, थोड़ी देर के बाद जब उसमें से एक्स एटीएम बाहर निकल जाएगा या उसका कुछ पार्ट प्रोडक्ट में चेंज होगा, दैट टाइम द प्रेशर ऑफ ए विल बी हियर पी आई माइनस एक्स एटीएम ऑफ बी, एक्स एटीएम ऑफ सी. So now the total pressure will be here pi minus x, this one, plus x plus x. So overall the sum of pt is equals to pi plus x. So x is equals to pt minus pi. So if we want to determine the value of pa, that is equals to pi minus x, we have to put the value of x here. So the pa is equals to 2 pi minus pt. So we can replace the pa from equation number 19 by this unit 2 pi minus pt. So the K1 for the gaseous first order reaction will be here 2.303 log pi upon 2 pi minus pt. By putting the value of pi and pt and t, we can calculate the rate constant. So in this manner we can calculate the rate constant of gaseous first order reaction. The following now some of the NCERT problem based on this concept, integrated rate equation for gaseous first order reaction. Among them, the first problem is NCERT exercise question number 21. The following data were obtained during the first order thermal decomposition of SO2Cl2 at constant volume. SO2Cl2 जो है उसका डीकम्पोजिशन फर्स्ट ऑर्डर है और ये गैसियस रिएक्शन है क्योंकि रिएक्टेंट और प्रोडक्ट दोनों ही गैसियस फेज में है. द डाटा हैज़ बीन गिवन फॉर एक्सपेरिमेंट नंबर 1, एक्सपेरिमेंट नंबर 2. इन एक्सपेरिमेंट नंबर 1 एट टाइम 0 द टोटल प्रेशर इज 0.5 and in experiment number 2 when time reaches 100 second the total pressure is 0.6. Calculate the rate of the reaction when total pressure is 0.65 atm. ये क्वेश्चन ही कह रहा है कि दो एक्सपेरिमेंट का डाटा दे रखा है और आपको इस रिएक्शन का रेट ऑफ रिएक्शन निकालना है जबकि टोटल प्रेशर कितना हो 0.65 atm. Now how can we solve this equation? Now this is the solution. We know that K1 is equals to 2.303 upon T log Pi upon 2 Pi minus Pt. So here time will be 100 second. Pi initial pressure that was 0.5. So 2 pi, 2 into 0.5 pt, that has been given, that is in the first case, in the experiment number second, that is 0.6. Don't need to write here 0.65 right now. This is the conceptual question. यहाँ पर 0.65 की वैल्यू नहीं रखनी है, सिर्फ 0.6 ही रखेंगे हम लोग. क्यों नहीं रखना है आगे मैं एक्सप्लेन करता हूँ. So 2.303 upon 100 log 0.5 upon 0.4. When we put the value of log 5 and log 4, it comes 0.0969. The result of K1 is 2.23 into 10 raised to power minus 23 second inverse. Now we have to calculate rate. Rate means this is the first order reaction, so the rate in the terms of pressure will be the partial pressure of SO2Cl2. To calculate the partial pressure of SO2Cl2, we have the formula 2 pi minus pt. At this stage, pt we have to consider 0.65 atm. Now put the value of pt 0.65, so it will give the partial pressure of SO2Cl2 0.35. So rate is equals to K into partial pressure of SO2Cl2, so it will be result 7.805 into 10 raised to power minus 4 atm per second. So in this manner we can solve this question. Now the second problem, which is also based on this concept, that is decomposition of azoisopropane to hexane at 543 Kelvin. The following data is obtained. azoisopropane का हेक्सेन में डिकम्पोजिशन होता है तो ये डाटा आपको मिलता है. 0 डिग्री सेल्सियस पे उसका प्रेशर 35 mmHg है, 360 पे 54 है और 720 पे 63 है. नाउ कैलकुलेट द रेट कांस्टेंट. किस तरह से हम लोग रेट कांस्टेंट कैलकुलेट करेंगे? दिस इज द सॉल्यूशन. नाउ सेट अप द इक्वेशन. NH2CH CH3 whole twice, that is the formula of diisopropane. Convert into N2 plus C6H10. So initial pressure is Pi. Initial pressure of nitrogen and this alkane will be 0. So after time t, the pressure will be Pi minus X and XATM and XATM. Total pressure again Pt is equals to Pi minus X plus X plus X. So X is equals to Pt minus Pi. So the partial pressure of azoisopropane will be here Pt minus X, Pi minus X. So it is equal to Pi minus bracket Pt minus Pi. So it will be 2 Pi minus Pt. Again K is equals to 2.303 upon T log initial concentration upon final concentration. Replace this concentration term by the pressure. So it will be here K is equals to 2.303 upon T log Pi upon 2 Pi minus Pt. First we have to calculate the rate constant at 360. Put the value of Pi and Pt. It will be 2.17 into 10 raised to power minus 3 second inverse. Then at time 720, again we have to calculate K. Put the value of Pi 35, Pt will be here 63, because at time 720 second the pressure is 63, so we have to introduce 63 there. After solving the K, we will get 2.24 into 10 raised to power minus 3. So we have the two values for the rate constant. Now calculate average of these two values. We will find out 2.2 into 10 raised to power minus 3 second inverse. So in this manner we can solve the equation based on the integrated rate equation of gaseous first order reaction. I hope you have understand all these things. What is the importance of this gaseous first order integrated rate equation? How can we derive this formula, and how can we solve the problem based on this topic? Thank you so much.